Hello there, and welcome to the Sleepless Scientist, a quiet place where your thoughts are allowed to loosen their grip, and curiosity can move gently without urgency or pressure. Tonight, we are going to take a slow and careful journey into something that sounds alarming at first, but becomes strangely calming the longer you sit with it. The terrifying quantum paradoxes that seem to break reality itself. Before we begin, and only if you truly enjoy these slow, thoughtful explorations, I invite you to like this video, subscribe to the channel, or leave a comment sharing where in the world you're listening from and what time it is for you right now. It is always comforting to know that, scattered across the planet, there are so many quiet minds drifting through the same questions together. When you are ready, you might dim the lights, settle into a comfortable position, perhaps let a soft background sound fill the room, and allow your breathing to slow just a little. There is nothing here you need to solve, nothing you need to remember perfectly. If your mind wanders, that is not a problem at all. Wandering is part of the journey. Tonight, we will explore how the smallest pieces of the universe behave in ways that overturn our deepest assumptions about space, time, and reality itself. We will talk about particles that seem to be in more than one state at once, connections that stretch across vast distances without carrying messages, choices that appear to echo backward in time, and cosmic objects that challenge the very idea of information surviving the universe. And yet, somehow, these same strange rules quietly power the technology that surrounds us every day. This is not a story about panic or doom. It is a story about how reality may be far less rigid than we once believed, and how that softness, that uncertainty, might not be something to fear. So take a slow breath, let your thoughts settle like dust in a quiet room, and together, let us begin. For most of human history, the universe felt dependable. Not necessarily kind, not always predictable in detail, but fundamentally understandable in principle. If you rolled a stone down a hill, it would follow a path you could trace with your eyes. If you tossed a ball into the air, it would rise slow and fall back into your hand. If you missed, it would land somewhere specific, not everywhere at once, and not somewhere mysterious beyond your reach. This view of reality, shaped by what we now call classical physics, was built from everyday experience. Objects had positions, events had causes, effects followed causes in a neat, orderly sequence. If you knew enough about the starting conditions, at least in theory, you could predict what would happen next. The universe in this picture behaved like an intricate but honest machine. Imagine a vast clock, its gears interlocking with perfect precision. Each movement triggers the next. Nothing happens without a reason, and nothing arrives without travelling the space in between. This image of reality was so intuitive that it barely felt like a theory at all. It felt like common sense. Even time itself seemed straightforward. Moments lined up one after another like footsteps in fresh snow. The past was fixed, the future was open, and the present was a thin line between them. Space was a stage. Time was a flowing river, and objects were actors moving predictably across it all. This worldview was not just comforting, it was empowering. It allowed humans to build bridges, aim cannons, predict eclipses, and eventually send machines into space. The success of classical physics reinforced the idea that the universe, at its core, was rational in a way that matched the human mind. And perhaps the most important assumption of all was this: reality existed independently of us. The moon did not need to be looked at in order to be there. A tree falling in a forest did not require an audience to make a sound. The universe went about its business whether anyone was paying attention or not. This assumption is so deeply woven into our thinking that it feels almost invisible. Objects have properties. Those properties exist whether we measure them or not. The world is there first, and we come along later to observe it. In this calm, mechanical universe, distance mattered. If something influenced something else, the influence had to travel through space. No instant connections, no shortcuts, no hidden whispers between distant objects. Space separated things, and that separation meant something. It is worth lingering here for a moment, because this is the mental landscape most of us still inhabit without realizing it. Even today, when we hear the word physics, we often imagine formulas describing motion, forces pushing and pulling, and trajectories that can be drawn with clean, confident lines. We imagine answers that exist whether we ask the question or not. This picture of reality is not foolish or naive. It is incredibly effective at the scale of everyday life. Your chair does not flicker between existing and not existing. Your phone stays in one place when you put it down. The floor does not occasionally forget to support you. The universe, most of the time, behaves exactly as this classical story predicts, and that is what makes what comes next so unsettling. Because beneath this familiar surface, hidden far below the scale of atoms and dust and breathing bodies, the universe appears to follow a very different set of rules. Rules that do not merely add complexity to the classical picture, but quietly undermine its foundations. At the smallest scales, objects do not always have definite positions. Events do not always wait politely for causes, and the idea that reality simply exists, fully formed and independent of observation, begins to wobble in ways that are difficult to ignore. What is most surprising is not that these strange behaviours exist, but that they were discovered at all. They did not emerge from mystical speculation or philosophical puzzles. They emerge from careful experiments, from scientists trying to understand light, heat, and matter just a little more precisely than before. The universe did not announce its strangeness with thunder. It revealed it softly, through patterns that did not quite line up, through results that refused to behave as expected. And as physicists followed those clues, they found themselves stepping away from the comfortable clockwork universe into a reality that was far more flexible and far more mysterious than anyone had imagined. And so, as we let this familiar picture of a sensible universe rest gently in the background, we can begin to approach the first small crack in that certainty. A simple experiment, a few narrow openings, and a pattern that should not exist, but stubbornly does. There is a strange thing about the most powerful ideas we carry. They rarely announce themselves. They do not arrive with labels or explanations. They slip quietly into place, often so early in life that we mistake them for reality itself. By the time we're adults, these ideas feel less like beliefs and more like facts, as solid as the ground beneath our feet. One of these ideas is the belief that the world exists in a fully formed way, even when no one is paying attention to it. That objects have properties all the time, not just when they are measured. That a stone has a position, a speed, and a weight, whether or not anyone is there to notice those things. This feels so obvious that questioning it can sound almost childish. Of course, the moon exists when no one looks at it. Of course, your keys are still on the table when you leave the room. The universe does not need an audience to keep going. Closely tied to this is another assumption, one that feels equally natural. If something influences something else, that influence must travel through space. It must move from here to there, passing through the distance in between. No instant effects, no shortcuts. Space separates things, and that separation matters. Together, these two ideas form a quiet foundation beneath our everyday thinking. Reality exists independently, and influences move locally. We rarely name these assumptions. We simply live inside them. They shape how we imagine everything from falling apples to distant stars. They shape our sense of fairness, of cause and responsibility, even of personal identity. If things happen, they happen for reasons. If something changes, something must have acted on it. The universe, in this picture, does not cheat. And for centuries, every successful experiment seemed to agree. When early physicists studied motion, gravity, and light, they found rules that fit perfectly within these assumptions. Objects moved smoothly, forces weakened with distance, effects followed causes like footsteps following a walker. Even when the mathematics became complicated, the underlying story remained comforting. You could always imagine what was happening behind the scenes. You might not know the numbers, but you trusted that there was a clear answer waiting to be uncovered. The world felt like a book written in advance, and science was simply learning how to read it more fluently. But here is where something subtle begins to shift. As scientists started to probe smaller and smaller scales, they noticed behaviours that did not quite fit this story. At first, these were minor annoyances, measurements that refused to line up neatly, patterns that seemed slightly off, like a clock that runs perfectly most of the time but occasionally skips a beat. No one rushed to rewrite reality over this. The expectation was simple. The strange results must come from missing details. Perhaps the instruments were not precise enough. Perhaps there were hidden factors not yet accounted for. Surely the underlying picture was still intact. After all, why wouldn't it be? This confidence was not arrogance. It was earned. Classical physics had worked too well for too long to abandon lightly. The idea that reality itself might be incomplete, or that the act of measuring could play a deeper role than simple observation, felt unnecessary, even extravagant. And yet the universe continued to misbehave. Light sometimes acted like a wave, spreading out and overlapping with itself. Other times, it arrived in discrete packets, like tiny indivisible grains. Matter, which had always seemed solid and dependable, began to show similar dual behaviour. It was as if nature could not decide which story it wanted to tell. Still, many hoped that beneath this confusion lay a more familiar truth. Perhaps particles really did have definite properties all along, and we simply lacked access to them. Perhaps the universe was still local and realistic, but cleverly hiding its inner workings from us. This hope rested on a powerful intuition that there is always a single correct description of what is happening, whether or not we know it yet. That uncertainty reflects ignorance, not reality itself. It is worth noticing how deeply human this intuition is. We are storytellers by nature. We like beginnings, middles, and ends. We like causes that lead cleanly to effects. We like worlds that make sense even when we turn our backs on them. Quantum physics, as it slowly emerged, didn't immediately destroy these instincts. Instead, it placed gentle pressure on them. Each new experiment added a little more strain, like weight added carefully to a bridge that has never been tested in this way before. At first, the bridge held. But with every strange result, a quiet question grew louder. What if these assumptions are not laws of nature, but habits of thought? What if reality, at its most fundamental level, is not required to behave in ways that feel intuitive to creatures like us? This is not an easy question to sit with, especially at the end of a long day, when the mind is tired and looking for rest. But there is something oddly soothing about it as well. If reality is not as rigid as we imagined, perhaps it is also less demanding. Perhaps certainty is not something we need to cling to quite so tightly. For now, we do not need to answer this question. We only need to recognize that these hidden assumptions exist, quietly shaping how we interpret every experiment and every explanation. And as we begin to loosen our grip on them just slightly, we make room for the first truly strange discovery. A discovery that did not involve distant galaxies or extreme conditions, but a simple setup, a few narrow openings, and a pattern of light that refused to behave. Imagine a quiet room, dimly lit with a single source of light shining toward a solid barrier. In that barrier are two very narrow openings, close together, like two thin doorways cut into an otherwise impenetrable wall. Beyond the wall is a screen, waiting to record whatever arrives. At first glance, this setup seems almost boring. Light shines, it passes through the openings, it lands on the screen. There is nothing here that should trouble the universe. If light were made of tiny particles like grains of sand thrown toward the wall, the result would be straightforward. Some grains would pass through the left opening, some through the right. On the screen behind the wall, you would see two bright regions directly aligned with the two openings. Simple, predictable, comforting. But that is not what happens. Instead, the screen fills with a series of bright and dark bands, stretching outward like ripples frozen in time. These bands form an interference pattern, the kind you would expect if waves were overlapping, reinforcing each other in some places and cancelling each other out in others. This is exactly what water waves do when they pass through two gaps in a breakwater. The waves spread, overlap and interfere, creating a pattern of peaks and valleys. When light behaves this way, it looks unmistakably wave-like. At this point, there is still nothing deeply unsettling. Light, after all, had long been understood as a wave. It bends, spreads, and interferes. So far, so good. The real strangeness appears when the experiment is made quieter still. Instead of shining a continuous beam of light, the source is dimmed until photons, the smallest detectable units of light, are sent one at a time, not in a stream, not in a wave. One, then another, then another. Each photon travels alone, with enough time between arrivals that it cannot possibly interact with the others. If these photons were tiny particles, each one should pass through one opening or the other, hit the screen, and leave a single dot. Over time, those dots should accumulate into two simple clusters, one behind each opening. But that is not what happens. Each photon arrives as a single point, yes, but as more and more photons land, the same interference pattern slowly emerges. Bright bands, dark gaps, the unmistakable signature of overlapping waves. It is as if each photon is interfering with itself. This is the moment where classical intuition quietly gives up. A single object cannot go through both openings at once. A particle cannot split itself, explore multiple paths, and then recombine. At least not according to the rules we grew up with. And yet, the experiment insists otherwise. To make sense of this, physicists describe the photon not as a tiny bullet, but as something spread out, like a probability cloud. Before it is detected, it does not have a single, definite path. Instead, it exists in a superposition of possibilities, exploring all allowed routes at once. This does not mean the photon is confused or undecided. It means that, until an interaction forces a result, the description that best predicts what we will see includes multiple paths simultaneously. A helpful image is to imagine sound filling a room. A single note played on a violin does not travel along one narrow line. It spreads, reflects, overlaps with itself, and fills the space. Only when it reaches your ear does it produce a definite sensation. Until then, it is better described as a pattern than a point. The photon behaves in a similar way. It spreads through both openings as a pattern of possibility, even though it is detected as a single, localized event. This alone would be strange enough, but the experiment has another layer. If a detector is placed at the openings to determine which path the photon takes, the interference pattern disappears. The screen now shows exactly what classical intuition expects. two simple clusters of impacts aligned with the openings. Nothing about the physical barrier has changed. The distance, the light source, the screen are all the same. The only difference is that information about the photon's path is now available. When the path is known, the wave-like pattern vanishes. This is not because the photon is shy, or because it senses an observer watching. It is because the act of gaining path information involves an interaction. That interaction disrupts the delicate overlap of possibilities, leaving behind a single, definite outcome. A useful metaphor is a set of overlapping ripples on a still pond. If you gently place a stick into the water to trace one ripple's origin, you disturb the surface enough to erase the interference pattern. The ripples no longer overlap cleanly. The pattern collapses into something simpler. In the quantum world, information is not passive. Knowing something means that something physical has happened, and that physical interaction changes what can occur next. This experiment does not tell us that reality depends on human awareness. It tells us something subtler and more unsettling. It tells us that at very small scales, the universe does not commit to a single history until it is forced to do so by interaction. Before that moment, the best description we have is not a single story, but a collection of overlapping possibilities. This is the first clear crack in the classical picture. Not a dramatic explosion, but a quiet, persistent inconsistency. A pattern that appears where it should not. A single particle behaving as if it were many. And once this crack appears, it does not close again. It widens slowly and steadily as we begin to ask deeper questions. If a particle does not choose a path until it is measured, what does that say about the nature of reality itself? For now, we can let that question rest gently in the background. Like light spreading through two narrow openings, it does not demand an immediate answer. It simply forms a pattern, waiting to be noticed. At first, the lesson from the two narrow openings feels unsettling but manageable. Light behaves like a wave when left alone, and like a particle when forced to reveal its path. It is strange, yes, but perhaps not world-shattering. After all, many things behave differently when disturbed. A calm lake looks smooth until you toss a stone into it. A quiet room changes the moment a door opens. But the deeper message of this experiment is not about disturbance alone. It is about information, about what it means for the universe to know something, and what must quietly give way when that knowledge exists. To see this more clearly, imagine the setup again. The light source is steady. The barrier has two narrow openings. The screen waits patiently on the far side. Photons arrive one by one, each leaving a tiny mark. Over time, the familiar pattern of bright and dark bands slowly appears, as if drawn by an invisible hand. Now imagine placing a small device near one of the openings. Its job is simple. It does not block the light. It does not absorb it. It merely records which opening a photon passes through, left or right, nothing more. With this device in place, the pattern on the screen changes completely. The gentle bands dissolve. In their place appear two straightforward clusters of impacts, just as classical intuition would expect from particles travelling along definite paths. What is striking is that nothing dramatic has happened. No walls have moved. No forces have been applied to shove the photons around. The only difference is that path information now exists somewhere in the universe. This is where many people first feel tempted to invoke something mysterious. Perhaps consciousness plays a role. Perhaps the universe reacts to being observed. Perhaps reality itself is somehow aware. But quantum physics does not require any of that. The key is to understand that in this context, observation does not mean looking. It means interaction. It means that some physical system has become correlated with the photon's path in a way that, in principle, could be read later. A camera does not need a human to watch it. A sensor does not need a mind behind it. If information is stored even quietly, the universe has changed. A helpful way to think about this is to imagine writing with invisible ink. As long as the message remains invisible, different interpretations overlap. Once the ink is revealed, the ambiguity vanishes. The act of revealing does not merely uncover the message, it fixes it. In the quantum world, gaining information fixes certain possibilities while erasing others. Before path information exists, the photon's description includes multiple routes at once. These routes overlap and interfere, creating the delicate pattern on the screen. Once the path is known, even in principle, those overlapping possibilities can no longer combine. The interference disappears, not because someone looked, but because the conditions required for overlap are gone. This challenges a deeply held intuition. We tend to think of information as something passive, something that simply reflects reality. In daily life, knowing where your keys are does not change their location. Measuring the length of a table does not alter the table. At the quantum scale, information is not a mirror. It is an actor. To store information, something must interact. To interact is to leave a trace, and that trace reshapes what can happen next. This is why it is misleading to say that observation creates reality. A better way to say it is that interactions limit which realities remain possible. There is something quietly humbling about this idea. It suggests that reality is not a fixed script unfolding regardless of circumstance. It is more like an improvisation, constrained by the interactions that occur along the way. Think of a conversation between two people. Before words are spoken, many responses are possible. Once a sentence is said out loud, the conversation takes a particular path. Other replies, once possible, fade away. The act of speaking does not invent the conversation, but it does narrow its future. The quantum world behaves in a similar fashion. Before interaction, multiple outcomes coexist as possibilities. Interaction selects, not by choice or intention, but by correlation and constraint. This perspective also helps prevent a common misunderstanding. Quantum experiments do not imply that reality waits for human attention. The universe does not pause until someone looks. Stars formed and collapsed long before eyes evolved to see them. What matters is not awareness, but connection. Any interaction that records information even faintly plays the same role as a measurement. A stray particle, a bit of heat, a vibration in a nearby atom can all carry away information. And once that information leaks into the environment, the delicate overlaps required for interference dissolve. This gradual leaking of information is one reason why quantum behavior is so hard to observe in everyday objects. A coffee mug sits in a noisy environment, constantly interacting with air molecules, light and vibrations. Information about its state is being scattered everywhere all the time. There is no chance for overlapping possibilities to remain intact. In contrast, carefully isolated particles in laboratories can preserve those overlaps long enough for us to notice them. The strange power of being watched, then, is not mystical. It is physical. It is the power of information to shape what remains possible. And this power has echoes beyond physics. In the modern world, being observed often means being categorized, tracked, and reduced to data. Once information exists, it changes how systems behave, not because the systems are conscious, but because constraints have been added. In the quantum realm, those constraints erase interference. In society, they shape choices and outcomes in quieter, subtler ways. For now, it is enough to sit with the idea that information is not neutral, that knowing something, and in the deepest physical sense, is an action with consequences, and that the universe, at its smallest scales, responds not to attention, but to interaction. This realization prepares us for an even stranger twist. If information can erase interference, what happens if that information is later erased itself? Can the universe, in some sense, forget? By now, the universe has already slipped a little out of focus. Light does not always behave like a neat stream of particles, and knowing something about its path quietly reshapes what patterns can exist. Still, there is a temptation to believe that beneath all this strangeness, there must be a familiar answer waiting, that particles really do have definite states, and that the uncertainty we see is only a temporary fog. This is where the idea of superposition gently but firmly asks us to slow down. In everyday life, most things exist in one state at a time. A door is either open or closed. A light is either on or off. A coin tossed into the air may spin briefly, but the moment it lands, it settles into heads or tails. Even while it is spinning, we assume the outcome is already determined, just hidden from us by motion. Quantum systems do not behave like spinning coins. When a particle is described as being in a superposition, it does not mean that we simply lack information about its true state. It means that, until an interaction forces a result, the particle genuinely does not have a single definite answer to give. A helpful image is to imagine a musical chord rather than a single note. When several notes are played together, they coexist, blending into a richer sound. The chord is not undecided about which note it wants to be. It is fully and honestly all of them at once. Only when the music stops do we hear silence, not a delayed decision. In the quantum world, superposition is like that chord. Multiple possibilities coexist, not as guesses, but as part of the system's actual description. This is often difficult to accept because it clashes with how we think about knowledge. We are used to uncertainty meaning ignorance. If we do not know where something is, we assume it is somewhere specific, and we just have not found it yet. Quantum physics asks us to consider a stranger possibility. Sometimes there is no single, hidden answer waiting behind the scenes. This idea is formalized through what physicists call the wave function. But we do not need equations to understand its role. Think of it as a map of possibilities. Not a map that shows one location, but one that shows all the places something could meaningfully be found, along with how strongly each possibility contributes to what might happen next. As long as the system remains undisturbed, this map evolves smoothly, like a shifting landscape. Hills rise, valleys deepen, paths overlap. Everything is continuous, fluid and reversible. Then comes interaction. When a particle interacts with something else, whether a detector, another particle, or the surrounding environment, the smooth landscape abruptly changes. The system produces a single concrete outcome. One note is heard, one path is taken, one result appears. This transition is often described as collapse, but that word can be misleading. It suggests something dramatic, like a structure falling apart. In reality, what collapses is not the particle itself, but the range of possibilities we can meaningfully describe afterward. Before interaction, many outcomes were possible and relevant. After interaction, only one remains. This is the measurement problem in its quietest form. How does a world built from overlapping possibilities give rise to definite experiences? At what point does a system stop being a cloud of options and become a single fact? Schrödinger's cat was invented to make this tension impossible to ignore. A cat placed in a sealed box tied to a microscopic quantum event forces us to confront the uncomfortable implication. If the quantum description is taken seriously, the cat is neither simply alive nor simply dead until the box is opened. The point was never to suggest that real cats exist in a ghostly half state. The point was to highlight how difficult it is to draw a clean line between the quantum world and the everyday one. If superposition applies universally, where does it stop? One tempting answer is to say that superposition only applies to very small things. Electrons, photons, atoms, not cats, chairs, or planets. But experiments have steadily pushed quantum behaviour into larger and larger systems, blurring that boundary. Another answer is to say that the act of observation itself forces reality to choose. But as we have seen, observation is not about minds or awareness. It is about interaction and information, and interactions happen everywhere, all the time. This leads to a subtler picture. Superposition is not fragile because it is unreal. It is fragile because it is easily disrupted. Large objects interact constantly with their surroundings. Information about them leaks outward, scattering into the environment. The overlapping possibilities do not vanish in a dramatic instant. They simply fade from relevance. In this sense, the world we experience is not separate from the quantum one. It is the quantum world after it has been gently but relentlessly narrowed by countless interactions. There is something almost poetic about this. At the deepest level, reality may be generous, allowing many possibilities to coexist. What we experience is the result of that generosity being shaped, trimmed, and guided by contact. To live between answers, then, is not to exist in confusion. It is to exist in a state where the future is not fully written, and the present is not as rigid as it appears. For now, we do not need to decide whether this is unsettling or comforting. We only need to notice that the universe, at its foundation, seems less interested in committing early and more interested in remaining open until interaction makes choice unavoidable. This openness sets the stage for a deeper question. If a single particle can exist in overlapping states, what happens when two particles share those possibilities together, even when separated by vast distances? At this point in the journey, the idea of superposition has begun to settle in, not as something fully understood, but as something we can at least sit beside without panic. Particles can exist in overlapping possibilities. Interaction narrows those possibilities into a single outcome. The world we experience is shaped by countless quiet interactions happening all the time, and yet there is a lingering discomfort. It is one thing to accept that an electron or a photon behaves this way. These are distant, abstract things. We do not live our lives at the scale of electrons. We do not tuck photons into our pockets. Their strangeness feels contained, safely quarantined in laboratories and textbooks. But what happens when we take these same rules and let them climb the ladder of scale? This is where Schrödinger's cat enters the story, and despite its fame, it is often misunderstood. The cat was never meant to be taken literally. It was not a proposal, it was a protest. Erwin Schrödinger imagined a sealed box containing a cat, a tiny amount of radioactive material, a detector, and a mechanism that could release poison if the detector clicked. The setup was designed so that whether the poison was released depended entirely on a quantum event, something fundamentally unpredictable. If the quantum description were applied without exception, then before the box was opened, the system inside would exist in a superposition of outcomes. The atom would be both decayed and not decayed. The detector would be both triggered and not triggered, and by extension, the cat would be described as both alive and dead. This conclusion felt absurd, and that was exactly the point. Schrödinger was not suggesting that cats truly hover between life and death. He was highlighting a deep tension in the theory. If quantum rules apply universally, then they should not magically stop applying when systems become larger. But if they do stop somewhere, where is that boundary? The cat forces us to confront an uncomfortable question. Is the world made of two kinds of things? quantum and classical, governed by different rules? Or is there a single underlying reality that only appears classical because of how we interact with it? Our instincts pull us toward the first answer. We want a clean, dividing line, a place where quantum weirdness politely ends and everyday reality begins. Electrons on one side, coffee cups on the other. But nature does not seem interested in drawing that line for us. Over the years, experiments have demonstrated quantum behavior in systems larger and more complex than anyone once thought possible. Tiny mechanical resonators, molecules made of dozens of atoms, even carefully isolated vibrations in solid objects have shown signs of superposition and interference. Each time, the boundary retreats. This does not mean that cats are secretly quantum ghosts. It means that the reason cats behave classically has less to do with size itself and more to do with interaction. A cat is not isolated. It is warm, noisy, breathing, moving, exchanging energy and information with its surroundings constantly. Every whisker twitch, every molecule of air, every photon of heat carries information away. The delicate overlaps required for superposition do not survive this onslaught, not because they are forbidden, but because they are drowned out. This gradual loss of overlapping possibilities is known as decoherence, though we do not need that word to grasp the idea. It is simply the process by which a system becomes so entangled with its environment that its many possible states can no longer interfere with one another in any meaningful way. Imagine a whisper in a silent room. Every subtle nuance is audible. Now imagine the same whisper in the middle of a crowded street. The sound is still there, but it is overwhelmed. The message has not vanished, but it has become effectively inaccessible. In the same way, the quantum possibilities of a macroscopic object do not disappear in a dramatic collapse. They are washed away by the constant noise of interaction. This reframes the cat not as a paradox about life and death, but as a lesson about scale, isolation, and information. The quantum world does not end. It fades. There is something unexpectedly calming about this picture. It suggests that the universe is not broken or contradictory. It is layered. At its foundation, it allows for generosity, for multiple possibilities to coexist. At larger scales, that generosity is constrained by connection. The world we experience is not separate from the quantum world. It is the quantum world after it has been gently forced to make up its mind. Schrödinger's cat lingers in popular imagination because it feels shocking, but its true value lies in how quietly it redirects our thinking. It tells us that certainty is not the starting point of reality. It is an outcome, and that outcome depends not on observation in the human sense, but on how deeply a system is woven into its surroundings. Once we let go of the idea that cats are secretly suspended between states, the thought experiment becomes less grotesque and more illuminating. It becomes a reminder that the universe does not care about our categories. It does not label things as small enough for uncertainty or large enough for definiteness. It responds only to interaction. This insight prepares us for an even more unsettling idea. If overlapping possibilities can be shared within a single particle, they can also be shared between particles. Not by sending signals or forces across space, but by forming a connection that ignores distance altogether. And when that connection appears, our last remaining sense of separateness begins to dissolve. Up to now, the strangeness of the quantum world has stayed mostly contained within single systems. One particle spreads through space as overlapping possibilities. One experiment reveals a pattern that disappears when information enters the picture. Even Schrödinger's cat, unsettling as it sounds, is still a story about a single box, a single system, interacting with its surroundings. But the universe has another surprise waiting. one that does not just blur certainty, but quietly challenges the idea that things are separate at all. This surprise appears when two particles become linked in a very particular way. Imagine two tiny objects created together in the same event. They move apart, drifting in opposite directions, perhaps toward opposite ends of a laboratory, or even far beyond, toward different corners of the universe. At first glance, they seem completely independent. Each occupies its own region of space. Each can be measured separately. Distance, it would seem, has done its job. And yet, when these particles are entangled, they no longer carry independent stories. Instead, they share a single description. Not in the sense that one sends messages to the other, but in the sense that their properties are defined together as parts of one combined whole. A useful metaphor is to imagine a pair of gloves placed into two boxes. One box is sent to the left, the other to the right. You do not know which glove is in which box until you open one. The moment you see a left glove, you instantly know that the other box contains a right glove. No signal needs to travel. The information was already there. At first, this sounds almost ordinary, but the quantum version is subtler. In the glove example, each glove already has a definite identity before the boxes are opened. You're merely discovering what was already decided. In quantum entanglement, there is no such hidden certainty waiting to be revealed. Before measurement, neither particle possesses a definite value on its own, only their relationship is well defined. It is as if the universe has written a rule that says, these two outcomes must match in a certain way, without deciding what either outcome will be individually. The particles are not carrying answers, they are carrying a promise. When one particle is measured, the shared description resolves into a pair of definite results. And remarkably, this resolution happens no matter how far apart the particles are. This is what troubled Albert Einstein so deeply. He famously referred to it as spooky action at a distance, not because he believed in ghosts, but because it seemed to violate a principle he held dear. Nothing, he believed, should influence something else faster than light can travel. If measuring one particle instantly determines the state of another distant particle, then either information is travelling impossibly fast, or something about our understanding of reality is incomplete. Einstein hoped for a third option. Perhaps the particles carried hidden instructions from the moment they were created. Perhaps each particle already knew how to respond to any possible measurement, and the appearance of instant connection was just an illusion. This idea is appealing because it preserves the familiar picture. Reality exists independently. Properties are definite, even if unknown. Distance still matters. For a time, this hope remained alive, but the universe had other plans. Careful experiments showed that no theory based on pre-existing hidden answers could reproduce the correlations seen in entangled particles. The results were too strong, too coordinated, too precise. Nature was doing something that classical intuition could not imitate. What makes this especially strange is that, despite these strong correlations, entanglement cannot be used to send messages. You cannot choose the outcome of a measurement on one particle to control the result on the other. Each measurement appears random on its own. Only when the results are later compared does the pattern emerge. This distinction is crucial. Entanglement creates connection, not communication. A helpful image is to imagine two musicians improvising together without hearing each other. Each plays notes that sound random in isolation. But when their recordings are played side by side, a hidden harmony appears. The coordination was built into the structure of the performance, not transmitted note by note. In the quantum world, entanglement weaves such harmonies into reality itself. This challenges our sense of separateness in a profound way. We're used to thinking of objects as self-contained units, interacting through forces that weaken with distance. Entanglement suggests that, at a fundamental level, the universe may be less like a collection of individual things and more like a web of relationships. The properties we measure do not always belong to objects alone. Sometimes they belong to the connection between objects. This idea can feel deeply unsettling, especially when we're tired and looking for rest. But there is also something gently reassuring about it. It suggests that connection is not an afterthought in the universe. It is woven in from the beginning. Entangled particles do not defy space by ignoring it. They reveal that space may not be the primary way reality organizes itself at the smallest scales. Relationships come first. Distance comes later. As we sit with this idea, it becomes clear why entanglement is more than a curiosity. It is a turning point. It forces us to reconsider what it means for something to be real, not as an isolated object with its own private properties, but as part of a larger, inseparable pattern. And this pattern leads directly to a question that physicists could no longer avoid. If entanglement produces correlations stronger than any classical explanation allows, how can we test whether reality truly behaves this way, rather than merely appearing to? To answer that question, philosophy had to step aside and experiment had to take the lead. By the time entanglement entered the conversation, physics had already crossed into unfamiliar territory. Particles could exist in overlapping possibilities. They could share a single description across vast distances, and the results of measurements, when compared later, lined up with an accuracy that felt almost intentional. For Albert Einstein, this was not merely strange, it was troubling. Einstein was no stranger to radical ideas. He had rewritten our understanding of space and time, showing that clocks tick differently depending on motion and gravity. He had revealed that mass and energy are deeply connected, two expressions of the same underlying thing. But through all of this, he held tightly to a few guiding principles about how reality should behave. One of those principles was locality. Locality is the idea that objects are only directly influenced by their immediate surroundings. If something changes here, the effect should spread outward gradually, limited by the speed at which information can travel. Nothing should leap across space instantaneously. Distance, in Einstein's view, was not a mere inconvenience. It was a fundamental feature of the universe. Entanglement appeared to threaten this idea. When two entangled particles are measured far apart, the outcome of one measurement is tightly linked to the outcome of the other. The connection seems to appear instantly, regardless of the distance between them. To Einstein, this suggested something deeply uncomfortable. Either information was travelling faster than light, or the particles carried hidden instructions all along. He preferred the second option. Along with his colleagues, Einstein proposed a way to preserve a more familiar picture of reality. Perhaps quantum mechanics was incomplete. Perhaps particles possessed additional properties that were not accounted for in the theory, properties that determine the outcomes of measurements in advance. We simply had not discovered them yet. In this view, randomness was an illusion. Uncertainty reflected ignorance, not indeterminacy. The universe, beneath its confusing surface, remained orderly and local. This idea became known as the concept of hidden variables. The name itself is revealing. It suggests that the answers are there, tucked away quietly, waiting to be uncovered. For many, this was a comforting possibility. It allowed quantum mechanics to remain a powerful tool without forcing a complete overhaul of reality. It preserved the idea that objects have definite properties, whether or not we observe them. And it kept distance meaningful, but comfort is not evidence. The challenge was to determine whether this hope could survive contact with experiment. Could any theory based on hidden, pre-existing properties reproduce the strange correlations seen in entangled particles? Or was the universe truly behaving in a way that no classical story could explain? For a long time, this question remained in the realm of philosophy. It was debated in letters, papers, and conversations, but seemed difficult to test directly. How could one distinguish between a genuinely non-local universe and one that merely appeared that way because of hidden details? Then came a remarkable insight. It turned out that one could derive a clear boundary between what any local, realistic theory could produce and what quantum mechanics predicted. This boundary was not an equation to be solved in your head, but a limit on how strong correlations could be if reality behaved according to classical assumptions. Think of it as a speed limit, not for motion, but for coincidence. If particles carried pre-written instructions and were only influenced locally, then no matter how cleverly those instructions were arranged, the correlations between distant measurements could not exceed a certain strength. That limit acted like a fence. Anything beyond it would signal that the classical picture had failed. This idea transformed the debate. The question was no longer philosophical, it was empirical. When experiments were finally performed with ever-increasing precision and care, the results were unambiguous. The correlations produced by entangled particles crossed the classical limit. Again and again, in different laboratories, with different particles, over increasing distances. Nature did not respect the fence, and yet something even more intriguing emerged from these experiments. Despite the strength of the correlations, they could not be used to send messages. Each measurement result, taken on its own, appeared random. There was no way to control the outcome on one side to influence the result on the other in a meaningful way. This preserved a crucial aspect of Einstein's worldview, even as it undermined another. Information still did not travel faster than light. Causality remained intact. What failed was the idea that reality could be both local and fully defined in advance. In a sense, the universe offered a compromise. It allowed deep connections across space, but refused to let those connections be exploited for communication. It revealed a structure richer than classical intuition, yet carefully balanced to avoid outright contradiction. For Einstein, this outcome was deeply unsatisfying. He famously remarked that he believed the moon exists even when no one is looking at it. Entanglement challenged that belief, not by denying the moon's existence, but by showing that the properties of things might not be as independent as we assume. What emerges from this story is not a victory of one thinker over another, but a shift in perspective. Einstein's unease was not a failure of imagination. It was a sign that quantum mechanics was pressing against the boundaries of how humans naturally think about reality. And that unease remains with us. Even today, physicists speak carefully about what entanglement means. Some emphasize the loss of classical realism. Others focus on the primacy of relationships over objects. Still others search for deeper theories that might reconcile these ideas in unexpected ways. What is clear is that the universe does not offer easy answers. It resists being reduced to familiar categories. It invites us to loosen our grip on certainty, while still rewarding careful, patient inquiry. As we let Einstein's discomfort settle gently in the background, we can appreciate what makes this moment so important. The strangeness of entanglement is not an isolated oddity. It is a signpost, pointing toward a deeper restructuring of how reality itself is organized. And to follow that signpost, physicists had to take a final step. They had to turn this unease into a test, one that would force the universe to choose between comforting assumptions and experimental truth. For a long time, the debate surrounding entanglement lived in an uncomfortable space between physics and philosophy. On one side stood the predictions of quantum mechanics, strange but precise. On the other stood a deeply rooted intuition about how the world ought to behave. Objects should have properties. Causes should not outrun space. Reality should not depend on distant events. Einstein's unease captured this tension perfectly. He did not deny the success of quantum theory. He questioned whether it told the whole story. What changed everything was the realization that this was not a matter of taste or interpretation. It was something the universe itself could answer. The key insight was simple but powerful. If the world truly behaved according to classical assumptions, if objects carried definite properties all along and were only influenced by their immediate surroundings, then there was a strict limit to how strongly distant events could be correlated. No clever arrangement of hidden instructions could exceed that limit. This idea did not require us to know the hidden details. It only required us to accept that such details existed and behaved locally. From those assumptions alone, one could derive a boundary, a kind of ceiling on coincidence. You can think of this ceiling as a fairness rule. Imagine two people separated in different rooms, answering yes or no questions without communicating. They might coordinate their answers in advance, agreeing on a shared strategy. But no matter how clever that strategy is, there is a maximum level of agreement they can achieve. Beyond that, coincidence would no longer be explainable by preparation alone. In the quantum case, this ceiling is known as a Bell limit, though we do not need to remember the name. What matters is the idea behind it. Classical reality, with all its hidden details and local influences, cannot produce correlations stronger than a certain threshold. Quantum mechanics predicts that entangled particles can cross that threshold. This transformed a philosophical puzzle into an experimental challenge. All one had to do was prepare pairs of entangled particles, measure them in carefully chosen ways, and compare the results. If the observed correlations stayed below the classical ceiling, Einstein's hope for a deeper, hidden order could survive. If they exceeded it, something fundamental would have to give. When the experiments were finally carried out, the universe answered clearly. The correlations went beyond what any local, realistic explanation could produce. Not once, not occasionally, but consistently. Over decades, with improving technology and increasing precision, the results held firm. Nature crossed the classical boundary with ease, and yet there was something remarkably restrained about this violation. Despite producing stronger than classical correlations, the outcomes of individual measurements remained unpredictable. You could not choose how one particle would respond in order to control the result of its partner. Each side, taken alone, looked random. Only when the data were brought together later did the pattern reveal itself. This is a subtle but crucial point. Quantum mechanics breaks classical intuition without breaking causality. It allows deep connections, but not messages. Correlation does not become communication. A useful metaphor is to imagine two shuffled decks of cards prepared in a special way. Each draw from either deck looks random, but when you compare the sequences afterward, you discover a striking alignment. The order was not communicated during the drawing. It was woven into the structure from the beginning. In the quantum world, that structure is not a set of hidden answers. It is a shared description that only resolves when interaction occurs. The implications of this are profound. At least one cherished assumption must be abandoned. Either reality does not consist of pre-existing properties, or influence is not confined to local neighborhoods, or both. The universe refuses to fit neatly into the boxes we prepared for it. What is remarkable is how calmly this conclusion emerges. There is no dramatic explosion, no sudden contradiction, just a quiet mismatch between expectation and result, repeated often enough that denial becomes impossible. This is why Bell's insight is often described as a turning point. It did not add a new phenomenon, it clarified the stakes. It forced physicists to confront the fact that quantum mechanics was not merely incomplete classical physics. It was something fundamentally different. And this difference is not abstract. It lies at the heart of technologies that now shape our world. Quantum encryption relies on the same correlations that defy classical explanation. Quantum computing draws power from states that cannot be described as collections of independent parts. The very features that once seemed like theoretical embarrassments have become practical resources. There is something quietly poetic in this. The universe reveals its deepest truths not by shouting, but by refusing to cooperate with our assumptions. It invites us to test, to question, and to listen carefully to what the results are telling us. As we absorb this lesson, we begin to see that the strange behaviour uncovered by the two narrow openings and the entangled pairs is not a collection of isolated oddities. It is part of a consistent, if unfamiliar, way the world organises itself. And once we accept that, another question naturally arises. If the strength of quantum correlations is real, and if information itself plays such a central role, what happens when we begin to make choices about measurement after events seem to have already unfolded? Does the universe keep a record of its past, waiting to be revealed? Or is the story of what happened still, in some sense, being written? After the experiments were done, after the data were compared and rechecked, there was a quiet moment in physics. Not a celebration, not a crisis, but something closer to a pause. The universe had answered the question it was asked, and the answer was inconvenient. The correlations were real. They exceeded what any classical explanation could allow. They appeared reliably, regardless of distance, orientation, or experimental detail. And yet, they did not allow messages to be sent faster than light. The world had revealed itself to be connected in a way that was subtle, disciplined, and deeply unfamiliar. So something had to give. The uncomfortable truth was that the classical picture relied on two assumptions that could no longer stand together. The first was that physical properties exist in a definite way before they are measured. The second was that influences are local, confined to their immediate surroundings. Quantum experiments insisted that you could not keep both. This was not a failure of logic or experimental technique. It was a structural feature of reality itself. The universe had drawn a boundary, not with force, but with consistency. To understand what this means, it helps to imagine a carefully balanced structure, like a stone arch. Each stone supports the others. Remove one, and the arch may still stand. Remove two, and it collapses. Classical intuition rested on a similar balance. Definite properties and local influence reinforced each other. Together they formed a stable picture of the world. Quantum mechanics removed one of those stones. The universe did not tell us which assumption to abandon. It simply showed that holding on to both would lead to contradictions. Different interpretations of quantum theory choose different ways forward. Some loosen the idea that properties exist independently. Others accept a form of non-local connection. Still others reshape the meaning of reality itself. What they all agree on is that the old picture cannot be restored. This realization can feel unsettling, especially when we are tired and seeking rest. But there is another way to hear it. The universe is not broken. Our expectations were incomplete. The classical world we experience is still there. Tables remain solid. Clocks still tick. Causes still precede effects in ways we can rely on. Quantum mechanics does not dissolve the everyday world into chaos. It explains why that world feels stable at all. The key is scale and interaction. At large scales, systems are constantly interacting with their surroundings. Information about their states leaks outward relentlessly. The overlapping possibilities that characterize the quantum world are quickly suppressed, not erased, but rendered irrelevant. What remains is a single, consistent outcome that aligns with classical intuition. In this sense, classical reality is not fundamental, it is emergent. It is what the quantum world looks like after it has been narrowed by countless interactions. There is something oddly reassuring about this. It means that the certainty we experience is not an illusion, but a consequence of connection, complexity, and time. It also means that the quantum world is not hostile to understanding. It simply asks us to shift our perspective. Instead of imagining reality as a collection of tiny objects carrying fixed properties, we are invited to think in terms of relationships, possibilities, and constraints. This shift can be difficult, but it is not unnatural. We already accept similar ideas in other domains. A person is not defined solely by isolated traits, but by relationships, context, and history. A melody is not a single note, but a pattern unfolding over time. Meaning emerges from connection. Quantum mechanics suggests that physical reality may work the same way. One of the most important lessons from this turning point is restraint. The universe allows deep connections, but it enforces limits. It permits correlations that transcend distance, but it forbids their use for signaling. It relaxes classical realism, but preserves causality. It bends intuition without breaking coherence. This balance is not accidental. It is what makes the theory workable, testable, and compatible with everything else we know about the universe. It is also what makes quantum mechanics so powerful. The very features that once seemed like philosophical liabilities have become practical tools. Quantum encryption uses the impossibility of copying unknown states to guarantee security. Quantum sensors exploit delicate superpositions to achieve extraordinary precision. Quantum computers aim to harness overlapping possibilities to explore solutions unreachable by classical machines. In each case, the strange structure of reality becomes a resource. But before we rush ahead to applications, it is worth lingering with the deeper implication. The universe does not offer a single, simple picture of itself. It offers a framework that adapts to scale, context, and interaction. What is true in one description may be incomplete in another, without either being wrong. This does not mean that reality is subjective. It means that it is layered. At the deepest level, possibilities coexist. At the level of experience, outcomes are definite. Between these layers lies interaction, information, and time. Understanding this helps us approach the next set of questions with a calmer mind. If the universe can relax its grip on definiteness and locality without collapsing into contradiction, what does that mean for our understanding of time itself? If choices made during measurement matter so deeply, when do they matter? And how far back does their influence reach? These questions do not lead us into fantasy. They lead us into carefully designed experiments that probe the structure of time in ways that feel almost paradoxical, yet remain grounded in observation. And as we move toward those experiments, we do so not as witnesses to a broken reality, but as guests in a universe that is more flexible, more connected, and more subtle than we ever imagined. Once the universe has shown that reality cannot be fully defined in advance, it becomes natural to ask a quieter, more unsettling question. If outcomes depend so deeply on interaction, on what information is available and when, then at what point does the universe decide what has happened? Is the past a fixed record, patiently waiting to be revealed? Or is it something more flexible than we are comfortable admitting? This question does not come from imagination alone. It comes from experiments designed with almost playful care, experiments that seem to ask the universe to make up its mind after the fact. To understand the heart of the issue, it helps to return, briefly and gently, to the familiar setup with two narrow openings. A particle leaves a source, passes through a barrier, and arrives at a screen. If we do nothing to learn which path it took, an interference pattern appears. If we gather path information, the pattern disappears. So far, the story feels consistent. Now imagine changing the order of events. Suppose the particle has already passed through the openings. Suppose it is already well on its way to the screen. Only after that do we decide how we will measure it. Only then do we choose whether to preserve the conditions needed for interference or to extract path information. Classical intuition protests immediately. The particle must have already chosen a path. The past is the past. Our late decision should not be able to reach backward and change what has already happened. And yet, when the experiment is performed, the results follow the choice of measurement, not the imagined history of the particle. If the experimental setup is arranged to preserve interference, the familiar pattern appears. If it is arranged to reveal path information, the pattern vanishes. The timing of the choice does not matter. The particle's behavior aligns with how it is measured, even when that choice is made after it has passed the critical point. This does not mean that the particle is travelling backward in time. Nothing is being rewritten. No signal is sent into the past. Instead, it reveals something subtler about how quantum descriptions work. In the quantum view, the particle does not carry a fully formed story of its journey. There is no hidden record that says, "I went left" or "I went right," waiting to be uncovered later. The description remains open, incomplete, until interaction closes it. A helpful image is to imagine a story told in pencil rather than ink. The outline exists, but the details are not fixed until the final edit. Reading the ending does not change the earlier chapters. It simply determines which version of the story becomes the one that is shared. In these delayed choice experiments, the universe is not revising the past. It is revealing that the past was never specified in the way we assumed. This idea can feel deeply unsettling because it challenges one of our most comforting beliefs, that time flows in a clean, linear way, leaving behind a trail of settled facts. Quantum mechanics suggests that at very small scales, some aspects of that trail remain softly undefined until they are brought into contact with the present. What matters is not when a choice is made, but how it constrains the possible descriptions of the system as a whole. This perspective also helps prevent a common misunderstanding. These experiments do not grant us the power to manipulate history. We cannot send messages to the past or change outcomes that have already been recorded. The results remain consistent with causality and the limits of information flow. Instead, they invite us to rethink what we mean by what happened. In everyday life, this distinction rarely matters. Our interactions are constant and noisy. Information leaks everywhere. The world around us is continually being measured by its environment. The past becomes fixed almost immediately. At the quantum scale, where systems can be carefully isolated, that fixation is delayed. Possibilities remain open longer, and the line between past and present becomes less sharp. There is something strangely calming about this once the initial shock fades. It suggests that reality is not rushing ahead, committing to details before it has to. It waits, it remains flexible, it responds to interaction rather than prediction. Think of a photograph slowly developing in a dark room. The image is there in potential, but it only becomes visible when the right process is applied. The timing of that process does not change the scene that was photographed. It determines which image becomes clear. Delayed choice experiments show us that quantum systems behave in a similar way. The structure of possibilities evolves smoothly. Measurement reveals a particular pattern, not by reaching into the past, but by selecting which description becomes meaningful. This also deepens our understanding of the role of information. Information is not just something we extract from reality. It is part of how reality organizes itself. When information becomes available, it reshapes what can be said about the system as a whole. As we sit with this idea, we begin to see a theme emerging. Again and again, quantum mechanics invites us to let go of the notion that reality is a collection of fully defined events unfolding independently of observation. Instead, it presents a world where description, interaction, and outcome are tightly intertwined. This does not make the universe arbitrary, it makes it responsive, and that responsiveness prepares us for an even more delicate experiment. If making information available erases interference, what happens if that information is later erased or rendered inaccessible? Can the universe, in some sense, restore the patterns it once suppressed? This question leads us not into speculation, but into one of the most carefully crafted and misunderstood experiments in modern physics, an experiment that feels like it toys with time itself, yet remains firmly rooted in the rules we have already encountered. By now, a quiet pattern has begun to emerge. Time does not behave quite as we expect. Outcomes are not always fixed in advance. Information, once available, reshapes what can be meaningfully described, and choices made later can determine how earlier events are understood without rewriting history or breaking causality. With that in mind, the next experiment feels almost inevitable. If gaining information about a particle's path destroys interference, what happens if that information is never actually used? Or more strangely, what if it is created and then carefully erased? At first, this sounds like a trick. Information once recorded should leave a permanent mark. After all, in everyday life, you cannot unring a bell. A footprint in wet sand remains even if no one looks at it. The past, we believe, accumulates evidence. But in the quantum world, evidence is more fragile than we assume. To explore this, physicists design an experiment that extends the familiar two-opening setup in a subtle way. Instead of sending a single particle toward the openings, they send a pair of particles created together, linked by entanglement. One particle heads toward the barrier with two openings. Its partner travels along a separate path toward a different detector. The first particle behaves just as before. If nothing reveals which opening it passes through, interference is possible. If path information exists, interference disappears. The twist lies in where that path information goes. In this setup, the information about which opening the first particle used is not stored locally at the barrier. Instead, it becomes encoded in the state of the second distant particle. The universe, in effect, spreads the information across the pair. If the second particle is measured in a way that preserves that path information, the interference pattern vanishes when we later compare the data. If it is measured in a way that scrambles or erases that information, something remarkable happens. The interference pattern returns, not on the screen directly. The screen always shows a jumble of impacts. But when the data are sorted according to how the second particle was measured, clear interference patterns emerge within the correlated subsets. This is the quantum eraser. It does not undo the past. It does not send signals backward in time. It does something far subtler. It determines whether path information is available anywhere in the system, even in principle. If the information exists, even unused, interference is lost. If the information is erased before it can be meaningfully accessed, interference can reappear in the correlations. A helpful metaphor is to imagine two notebooks written in invisible ink. As long as the writing remains invisible, multiple interpretations overlap. If one notebook is treated in a way that reveals the writing, the ambiguity vanishes for both. But if the ink is smeared or chemically neutralized before it becomes readable, the overlapping interpretations remain. In the quantum case, erasing information does not mean destroying a record after the fact. It means ensuring that no record ever becomes available, in a form that distinguishes one path from another. This is why timing can feel misleading in these experiments. The decision about how to measure the second particle can be made after the first particle has already been detected. And yet, the presence or absence of interference in the correlated data aligns with that later choice. Once again, the universe is not changing what happened. It is clarifying what kind of description applies. The first particle never had a single, definite path stored somewhere in secret. It had a set of possibilities, constrained by how information flowed through the system as a whole. Whether those possibilities could interfere depended on whether distinguishing information existed anywhere. This challenges a deeply ingrained assumption. We tend to think of information as something that belongs to us, something we gather and interpret. The quantum eraser shows that information is physical. It belongs to the universe itself, and the universe behaves differently depending on how that information is distributed. There is something quietly profound in this. It suggests that reality is not built from events alone, but from the structure of information linking those events. What matters is not just what happens, but what could, in principle, be known. This does not mean that knowledge creates reality. It means that the availability of information constrains the kinds of patterns that can exist. In everyday life, this distinction is invisible. Information spreads rapidly and irreversibly. Records accumulate. Histories harden. The quantum eraser requires extreme care to isolate systems and control how information flows. It reveals something that is normally drowned out by noise, and once seen, it cannot be unseen. The quantum eraser does not tell us that the universe is magical or arbitrary. It tells us that the classical idea of a fixed observer-independent history is an approximation, a very good one, but an approximation nonetheless. At small scales, history is not a single line etched into stone. It is a branching structure of possibilities, pruned and shaped by interaction and information. This realization also helps us let go of unnecessary mysticism. There is no retroactive causation, no rewriting of time. The rules remain consistent. What changes is our understanding of what was ever definite in the first place. As we allow this idea to settle, a deeper pattern comes into view. The quantum world does not resist understanding. It resists being forced into categories that were never meant for it. And that brings us to a final, unsettling boundary. If information plays such a central role in shaping reality at the smallest scales, what happens in the most extreme environments the universe has to offer? Places where gravity is overwhelming, time itself bends, and information seems to vanish beyond any possible retrieval. To answer that, we must turn our attention to objects so dense and so distant that even light cannot escape them. Objects that push our understanding of reality to its absolute limit. Up to this point, the story of quantum paradoxes has unfolded in carefully controlled environments, quiet laboratories, isolated particles, delicate experiments designed to preserve fragile possibilities just long enough for us to glimpse them. Information has played a central role, shaping what patterns appear and what histories can be meaningfully described. But there is one place in the universe where information seems to face a far more violent fate, a place where gravity overwhelms everything else, where space bends inward, where time itself slows to a crawl, a place from which no signal, no matter how fast, can return. This is where the question of information becomes not just strange, but terrifying. Black holes were once thought to be simple objects, dense remnants of collapsed stars wrapped in a boundary beyond which nothing could escape. If something fell in, it was gone forever. End of story. Classical physics had no problem with this. Information could be lost. The universe did not keep perfect records. What mattered was energy and motion, not the details of how things began. Quantum mechanics, however, tells a different story. In the quantum world, information is not optional. It cannot simply disappear. The equations that describe quantum evolution preserve information in the same way a perfectly reversible dance preserves every step. If information were truly destroyed, the entire framework would break. This creates a profound conflict. General relativity, our best theory of gravity, suggests that anything crossing a black hole's boundary is permanently hidden. Quantum mechanics insist that the information describing that thing must still exist somewhere, in some form. Both theories are extraordinarily successful. Both are supported by overwhelming evidence. And yet, in the presence of a black hole, they cannot both be right in the way we usually understand them. This is the black hole information paradox. To appreciate how deep this conflict runs, imagine burning a book. The pages turn to ash. The ink vanishes. At first glance, the information seems lost. But in principle, if you could track every particle of smoke and heat, every vibration of air, you could reconstruct the text. The information is scrambled, not destroyed. Black holes appear to do something far worse. When a black hole forms and later slowly evaporates through faint radiation, the radiation looks completely random. It carries no obvious imprint of what fell in. If the black hole eventually disappears entirely, where did the information go? If it is truly gone, quantum mechanics is wrong. If it is somehow preserved, then our understanding of black holes, space, or time must be incomplete. For decades, this question haunted theoretical physics. Some proposed that information escapes in subtle correlations hidden within the radiation. Others suggested that information remains stored at the boundary, like a cosmic memory etched onto the surface. Still others wondered whether information might survive in a way that radically reshapes our understanding of space-time itself. What makes this paradox especially unsettling is how it echoes earlier themes. Once again, we are forced to confront the role of information. Once again, our classical intuitions about space and locality begin to fail. And once again, the universe seems to insist that relationships matter more than isolated events. In the case of black holes, the relationships between gravity and quantum mechanics, two pillars of modern physics that rarely speak the same language. There is something deeply poetic about this tension. The most extreme objects in the universe, born from collapse and darkness, have become mirrors reflecting the deepest questions about reality. They force us to ask whether space is fundamental, whether time is absolute, and whether information is the true currency of the cosmos. Recent insights suggest that information may not be stored where we expect it, that the interior of a black hole and its boundary may be two descriptions of the same underlying structure, that what appears lost from one perspective is preserved from another. This does not mean the paradox is fully resolved, far from it. But it does suggest a direction, a hint that space-time itself may emerge from more fundamental patterns of information and connection. If that is true, then black holes are not exceptions to the rules of reality. They are signposts pointing beyond them, and here the terrifying aspect becomes clear. If space-time and locality are emergent, not fundamental, then the separations we rely on may be approximations, distance, inside and outside, before and after. These distinctions, so solid in daily life, may soften under extreme conditions. This does not make the universe chaotic, it makes it layered. At familiar scales, time flows forward. Causes precede effects. Information spreads gradually. At deeper levels, those rules may arise from something more subtle, something that only reveals itself when pushed to extremes. Black holes push harder than anything else we know. As we let this idea settle, it becomes clear that the information paradox is not an isolated problem. It is the culmination of the story we've been following all along. Superposition challenged definiteness. Entanglement challenged separateness. The quantum eraser challenged fixed history. Black holes challenge the very idea that information can be confined to a place. And yet, out of this challenge comes hope. The same insights that make black holes terrifying also make them powerful tools. By forcing us to reconcile quantum mechanics and gravity, they may guide us toward a deeper, more unified understanding of reality, one where information, not matter or space alone, plays the central role. As we approach the end of this journey, one final question remains. If reality is built from overlapping possibilities, deep connections, and conserved information, how should we think about the many outcomes that quantum mechanics seems to allow? Does the universe choose one reality and discard the rest? Or does it allow all possibilities to unfold, each in its own quiet way? To explore that, we must step into an idea that is as unsettling as it is strangely elegant. By now, the universe has asked us to loosen our grip on several comforting ideas. Outcomes are not always fixed in advance. Objects are not always independent. Information shapes reality more deeply than we once imagined, and in the most extreme places, even space and time may be emergent rather than fundamental. With all of this in mind, one final question quietly presses forward. When a quantum system has many possible outcomes, and measurement produces just one of them, what happens to the rest? Do they simply disappear? Are they erased from existence the way chalk dust is wiped from a board? Or do they persist in some form, hidden from us, continuing their own silent stories? This question leads to one of the most controversial and misunderstood ideas in modern physics, the many worlds interpretation. At first, the idea sounds extravagant, even reckless. It suggests that every time a quantum measurement occurs, the universe does not collapse into a single outcome. Instead, all possible outcomes continue to exist, each in its own branch of reality. Nothing is destroyed, nothing is selected. Everything that can happen does happen. To understand why anyone would take this seriously, we need to remember the problem it tries to address. Quantum mechanics describes the evolution of systems in a smooth, continuous way. Possibilities overlap and evolve predictably. The trouble appears only when measurement enters the picture. Suddenly, the smooth evolution seems to halt, replaced by a single, definite result. Where does that definiteness come from? Many Worlds offers a radical but internally consistent answer. It says that the smooth evolution never stops. There is no sudden collapse. Instead, the observer becomes part of the quantum system, entangled with the outcome. The universe splits, not violently but quietly. Each branch contains a version of the observer who experienced one particular result. From the perspective of that observer, the outcome feels singular and final. The other branches are inaccessible, not because they vanished, but because they no longer interact. A useful image is to imagine a river approaching a delta. The water divides into many channels, each flowing smoothly onward. A leaf carried along one channel does not feel the existence of the others. Its journey is continuous, uninterrupted, and complete. In the many worlds view, reality behaves like that river. Branching is not an event. It is a natural consequence of continuous evolution. This interpretation has a surprising advantage. It removes the need for a special rule about measurement. The same laws apply everywhere, at all times. There's no mysterious moment when physics changes its behavior, but the cost is high. It asks us to accept that reality is far larger than anything we can experience. that countless versions of events, decisions, and outcomes coexist, even though we can access only one thread. This idea often triggers immediate resistance. It feels extravagant, wasteful. Surely the universe would not generate such excess without reason, and yet physics is not obligated to match our sense of elegance or economy. It is obligated to match observation. Many worlds does not predict new experimental results that differ from other interpretations. That is part of what makes it controversial. It is not chosen because it is testable in a new way. It is chosen because it takes the existing equations seriously, without adding extra assumptions. Whether one finds that admirable or unsettling often depends on temperament. There is also a more subtle discomfort. If all outcomes occur, what does probability mean? Why do we experience some outcomes more often than others? In the many worlds view, probability is not about chance in the usual sense. It is about proportion. Some branches are larger, more heavily weighted than others. Observers are more likely to find themselves in those branches, not because of randomness, but because of how the structure of branching unfolds. This is a difficult idea to fully grasp, and many physicists continue to debate whether it truly resolves the question or merely reframes it. There's also a darker implication that sometimes appears in popular discussions. The idea of quantum immortality, where an observer always finds themselves in branches where they survive. This notion is far more speculative and far less grounded than the core interpretation itself. It relies on assumptions that go well beyond what quantum mechanics actually says. What matters for our purposes is not the drama of endless universes, but the deeper shift in perspective. Many worlds invites us to stop thinking of reality as a single line of events, chosen from many possibilities. Instead, it asks us to think of reality as a structure that contains all those possibilities, with experience tracing out one path through it. This fits surprisingly well with the themes we have encountered before. Superposition allows many possibilities to coexist. Entanglement ties distant outcomes together. The quantum eraser shows that histories are not fixed until information is settled. Black holes suggest that space-time itself may emerge from deeper patterns. Many worlds is not an isolated leap, it is a continuation. Whether or not it is the final word remains an open question. Physics is still searching for a deeper theory that unites quantum mechanics with gravity, one that may reshape these ideas yet again. Many worlds could turn out to be a stepping stone, not a destination. But even as a stepping stone, it offers something valuable. It reminds us that the universe may be under no obligation to reduce itself to a single story, that what we experience as the world may be one thread woven through a much richer tapestry, and that our sense of finality may be a feature of perspective, not of reality itself. As we near the end of this exploration, one thought becomes clear. Quantum paradoxes do not shatter reality, they expand it. They show us that beneath the familiar surface lies a structure that is flexible, interconnected, and profoundly strange. And yet, this strangeness does not remain locked in theory. It powers technologies we rely on every day, devices that work precisely because reality behaves in this counterintuitive way. To understand how the terrifying becomes useful, how paradox becomes progress, we must take one final step. We must look at how these ideas leave the laboratory and quietly enter our lives. After wandering through uncertainty, connection, erased histories, and branching realities, it would be easy to believe that quantum mechanics lives only in the realm of thought experiments, a strange intellectual landscape, fascinating but distant from daily life, something to be admired quietly, then set aside. But the truth is far more intimate. The same paradoxes that unsettle our sense of reality are the reason much of the modern world works at all. Quantum mechanics is not a philosophical curiosity that survived despite its strangeness. It is a practical framework that thrives because of it. Every time you use a smartphone, look at a digital screen, or rely on modern medical imaging, you are benefiting from quantum behavior that refuses to act classically. These technologies work not in spite of superposition, uncertainty, and entanglement, but because of them. Consider the simple act of storing information. At the heart of every computer chip are materials whose electrical behavior cannot be explained without quantum mechanics. Electrons do not behave like tiny billiard balls flowing neatly through wires. They occupy energy levels, jump between them, and sometimes pass through barriers they do not have enough energy to cross in the classical sense. This phenomenon, known as tunneling, sounds almost magical when described abstractly. A particle appears on the other side of a barrier without crossing it in the usual way. But when softened into imagery, it becomes more intuitive. Imagine a ball rolling toward a hill. In classical physics, if the ball lacks the energy to reach the top, it rolls back down. In the quantum world, the ball is more like a fog than a point. A faint portion of that fog can appear on the other side of the hill, allowing the ball to emerge where it should not be. Modern electronics rely on this behavior. Without it, transistors could not be made small enough to power today's devices. The paradox of particles ignoring classical barriers becomes the foundation of reliable computation. Lasers offer another example. The clean, coherent light from a laser depends on atoms existing in carefully prepared quantum states. These atoms are encouraged to release photons in lockstep, producing light waves that march together rather than jostling randomly. This coordination arises from the same quantum rules that govern superposition and measurement. The laser does not fight quantum behavior, it choreographs it. Medical imaging, such as magnetic resonance scans, goes even further. These machines rely on the quantum properties of atomic nuclei, gently coaxing them into alignment and listening to how they respond. The images that result, revealing soft tissue with remarkable clarity, emerge from quantum behavior unfolding at a scale we can see. Even the very stability of matter depends on quantum rules. Without them, atoms would collapse, electrons spiraling into nuclei, chemistry dissolving before it could begin. The world would not merely look different, it would not exist in any recognizable form. In this sense, quantum mechanics is not an exotic layer added on top of reality. It is the quiet scaffolding that holds reality up. And now we are learning to push further. Quantum encryption uses the same sensitivity to information that erases interference patterns. Any attempt to intercept a quantum signal leaves a trace. Eavesdropping becomes visible not because of clever monitoring, but because reality itself refuses to hide the disturbance. Quantum computing takes this idea even deeper. Instead of bits that are either 0 or 1, quantum systems allow for overlapping possibilities. Calculations unfold across many potential paths at once, not by trying every answer in parallel like a crowd of workers, but by allowing possibilities to interfere, reinforcing correct paths and cancelling incorrect ones. This does not mean quantum computers think faster in a human sense. It means they explore problem spaces in a way that classical machines cannot imitate. Once again, the same features that once felt terrifying become tools. What is striking is how disciplined this strangeness remains. Quantum mechanics allows flexibility, but it enforces consistency. It permits uncertainty, but only within precise limits. It bends classical intuition without letting the world collapse into chaos. This balance is what makes the theory trustworthy. And perhaps that is the most important lesson of all. Quantum paradoxes do not tell us that reality is unknowable. They tell us that knowledge itself has a structure. that certainty is not always the starting point. Sometimes it is the result of interaction, scale, and time. As we grow more familiar with this idea, the fear begins to soften. The universe does not feel hostile or absurd, it feels patient, willing to reveal itself, but only if we are willing to let go of assumptions that no longer serve us. There is a quiet humility in this, the realization that our everyday intuitions, shaped by survival and habit, are not well suited to describing the deepest layers of existence. That does not make them wrong, it makes them local. Quantum mechanics invites us to expand our sense of what is reasonable, and in doing so, it gives us tools powerful enough to reshape the world, while reminding us that those tools are grounded in something far stranger and more beautiful than any machine. As we approach the final stretch of this journey, one last thought remains. If quantum paradoxes both unsettle and empower us, what do they ultimately say about our place in the universe? Are we observers peering into a reality that exists independently of us? Or are we participants, woven into the same web of interaction and information that defines everything else? To answer that, we must gently step back and look at the story as a whole. After seeing how quantum paradoxes quietly power the world around us, it becomes tempting to step back and ask a more personal question. Not about particles or equations, but about us. Where do we stand in all of this? For centuries, science encouraged a particular image of reality. The universe was a vast machine ticking along according to fixed rules. Objects existed independently. Events unfolded whether anyone was there to witness them or not. We were observers standing safely outside the system, peering in. Quantum mechanics gently but persistently dissolves that distance. It does not say that humans create reality by looking at it. That would be a misunderstanding. But it does say that interaction is unavoidable. To exist is to interact. To measure is to become entangled. There is no perfectly detached vantage point. Reality, at its deepest level, behaves less like a finished object and more like an ongoing conversation. A conversation does not exist independently of its participants. It is shaped by timing, context, and response. Words spoken early constrain what can be said later. Silence carries meaning, and once something is said aloud, it cannot be unsaid in quite the same way. Quantum interactions work similarly. When a system interacts with another, information flows, possibilities narrow, outcomes take shape. The universe responds not to intention, but to connection. This does not elevate observers to a privileged role. A detector, a molecule of air, a grain of dust participate equally. Consciousness is not required. Presence is enough. In this view, reality is not waiting to be revealed like a hidden photograph. It is continuously being refined by interaction, not invented, not imagined, but shaped. This idea can feel unsettling at first because it challenges the comfort of separation. We like to believe that the world is fully formed and that we merely uncover it piece by piece. Quantum mechanics suggests something subtler. The world is structured, lawful, and consistent, but it does not finalize every detail in advance. It leaves room. This room is not chaos. It is constraint without rigidity. It is order that emerges rather than order that is imposed. Think of a piece of music performed live. The score exists, the notes are written. But each performance is shaped by the acoustics of the room, the timing of the musicians, the energy of the audience. The structure is real, but the experience is co-created. Quantum reality behaves in a similar way. The laws exist, the patterns are reliable, but the specifics of how possibilities resolve depend on interaction. This perspective helps reconcile many of the paradoxes we have encountered. Superposition is not indecision, it is openness. Entanglement is not spooky influence, it is shared structure. The quantum eraser is not rewriting history. It is clarifying which descriptions apply. Black holes are not information graveyards. They are stress tests for our assumptions, and many worlds, whether ultimately correct or not, highlights an important truth. The universe does not seem eager to discard possibilities unless it must. There is something deeply humane about this picture, not because it centers us, but because it dissolves the illusion of isolation. We are not strangers in a cold, mechanical cosmos. We are participants in a web of interaction that extends from the smallest scales to the larger structures. Even time begins to look different through this lens. Instead of a rigid river flowing past us, time appears more like a framework for organizing change. Past, present, and future are not equally fixed at all scales. At everyday scales, the past is solid, the future open. At quantum scales, the distinction blurs. Histories remain soft until interaction firms them up. This does not rob time of meaning, it deepens it. It suggests that the present is not merely a point sliding along a timeline, but a moment where possibilities become commitments, where openness meets consequence. And this brings us back to something surprisingly simple. The terrifying aspect of quantum paradoxes is not that reality is unstable, it is that our assumptions were too narrow. We expected the universe to behave like our intuitions, shaped by survival on a warm, solid planet under gentle conditions. The universe had other plans, but those plans are not hostile, they are generous. They allow for connection, creativity, and emergence. They allow for a world that is stable enough to build civilizations, yet flexible enough to surprise us. As we reach the end of this long, quiet exploration, it becomes clear that quantum mechanics does not remove meaning from the universe. It relocates it. Meaning does not come from certainty alone. It comes from structure meeting openness, from rules that allow variation, from a reality that is not finished until it is lived. And perhaps that is the most comforting thought of all. The universe is not a frozen script unfolding without regard for context. It is a dynamic system, responsive and resilient, unfolding through interaction at every level. We are not outside observers looking in. We are threads in the fabric, participating simply by being here. As you rest with this idea, there is no need to resolve every paradox or choose a favourite interpretation. Quantum mechanics does not demand belief, it rewards patience. It asks us to sit with uncertainty, not as a failure of understanding, but as a feature of a deeper order, an order that remains consistent, testable, and quietly astonishing. And so, as this journey begins to settle, we can let the question soften. The universe does not require us to solve it tonight. It only invites us to notice how deeply we are already part of its ongoing conversation. As this long exploration begins to wind down, it helps to return to a quieter place, not to a laboratory or a black hole, but to the ordinary world you move through every day, the room you are in, the slow rhythm of your breathing, the gentle certainty that the floor beneath you will remain solid when you stand. Quantum mechanics does not take any of this away. Despite everything we have uncovered, the world you inhabit remains dependable. Chairs do not flicker between states. Clocks do not forget which hour it is. Causes still come before effects in the ways that matter for living, planning, and resting. What quantum paradoxes ask of us is not to abandon this stability, but to understand where it comes from. The universe is not rigid at its foundation. It is flexible, possibility rich, and yet, from that flexibility emerges a world that feels firm and predictable, not because uncertainty vanished, but because interaction narrowed it, not because mystery was erased, but because it was shaped. This realization allows us to live comfortably with a softer universe. A softer universe is not a weaker one. It is a universe that allows for nuance, one that does not insist on absolute answers where none are required, one that preserves consistency without demanding rigidity. In daily life, we already accept this kind of softness without noticing. A memory is not a perfect recording. It is a reconstruction, shaped by context and recall. A conversation does not have a single, immutable meaning. It unfolds differently depending on timing, tone, and response. Meaning emerges through interaction. Quantum mechanics suggests that reality itself may operate on similar principles, only far more precisely and reliably than our minds ever could. This perspective gently dissolves the fear that often surrounds quantum ideas. The fear that reality is unstable, that nothing is real until we look at it, that the universe is arbitrary or chaotic beneath the surface. None of that is true. Reality is structured. The rules are clear. The predictions are astonishingly accurate. Quantum mechanics is one of the most successful theories ever developed, not because it is vague, but because it is exact. What it relaxes is not lawfulness, but premature certainty. It tells us that some questions do not have answers until the right interaction occurs, that some properties do not exist in isolation, that some distinctions like past and future or inside and outside may depend on scale and context. This is not a flaw, it is an invitation to think less in terms of static objects and more in terms of relationships, less in terms of fixed outcomes and more in terms of unfolding processes. There is a quiet psychological relief in this if we let it settle. It suggests that uncertainty is not always a problem to be solved. Sometimes it's a space to be inhabited, a space where creativity, adaptation, and resilience can emerge. The universe, it seems, is not in a hurry to finalize everything. It allows possibilities to coexist until interaction makes choice unavoidable. It does not cling to one story when many are consistent with its rules, and in that sense the universe is remarkably patient. This patience is reflected in how slowly many quantum effects reveal themselves, how carefully experiments must be designed, how fragile superpositions are, how easily information leaks and collapses possibilities into classical outcomes. Quantum weirdness is not shouting at us all the time, it is whispering beneath the noise. When we isolate systems, when we quiet the environment, when we listen closely, we hear it. When we do not, the world behaves exactly as we expect. This balance is why quantum mechanics does not undermine trust in reality. It strengthens it. It shows us why the world is reliable without pretending that reliability is fundamental. The terrifying aspect of quantum paradoxes fades when we realize that nothing essential to living is threatened. What changes is our metaphysical comfort, not our practical footing. And perhaps that discomfort is healthy. It reminds us that our intuitions are local tools, shaped by evolution and habit, useful but not universal. It reminds us that understanding grows not by defending assumptions, but by letting them soften when evidence demands it. As you rest with these ideas, there is no need to hold them tightly. Quantum mechanics does not ask for belief, it asks for openness. You do not need to decide which interpretation is correct. You do not need to resolve the deepest paradoxes tonight. Even physicists do not agree on all of them. What matters is the shared lesson running quietly through everything we've explored. Reality is deeper than it appears, but not less trustworthy. More connected, but not chaotic. More flexible, but not arbitrary. It is a universe where information matters, where interaction shapes outcome, where possibility precedes certainty, and where certainty, when it arrives, is strong enough to build worlds. In that universe, we are not anomalies. We are natural expressions of the same principles, systems that interact, gather information, and experience definite outcomes moment by moment. There is something gently comforting in that thought. You're not standing on the edge of a broken reality. You're resting within a structured, lawful cosmos that allows room for both mystery and stability. As this exploration comes close to its end, it is worth noticing how the fear has softened. The paradoxes remain, the questions remain, but they no longer feel threatening. They feel like open doors. And beyond those doors is not chaos, but a deeper kind of order. One that does not demand certainty everywhere, all at once. One that allows reality to unfold at the pace of interaction. In the final moments of this journey, there is nothing left to prove, only something to appreciate. The universe is not what we once thought it was. And yet, it is still here, still consistent, still astonishingly reliable, and you are still safely within it. And so, we arrive at the far edge of this long, gentle journey, not at a final answer, but at a place of rest, a place where the questions no longer press urgently, and the paradoxes no longer feel sharp. At the beginning, quantum mechanics appeared terrifying. Particles in many places at once, connections that ignore distance, histories that refuse to settle until they are asked to, information that seems more fundamental than matter itself, even the suggestion that reality might branch, quietly and endlessly, beyond what we can ever observe. It is understandable that these ideas provoke unease. They challenge the instincts we rely on to move safely through the world. They loosen the firm edges of certainty that help us feel grounded, but now, having walked slowly through them, those same ideas appear in a different light. They are not signs of a broken universe. They are signs of a universe that is more subtle than our first impressions allowed. Quantum paradoxes do not tell us that nothing is real. They tell us that reality is not obligated to finalize itself before interaction requires it. They do not say that the world depends on us watching it. They say that connection matters whether or not anyone is aware of it. They do not erase time. They reveal that time, like space, may be part of a deeper structure that becomes clearer at some scales and softer at others, and perhaps most importantly, they do not isolate us from the universe. They place us firmly within it. You're not an observer hovering outside reality, peering in. You're a physical system among other physical systems, interacting, exchanging information, and experiencing definite outcomes moment by moment. The same rules that govern particles and photons also govern you, scaled up, smoothed out, made stable through constant interaction. There is something profoundly comforting in that continuity. It means that the ground beneath you feels solid, not because the universe pretends to be simple, but because complexity has a way of organizing itself into reliability. It means that the past feels fixed, not because possibility vanished, but because interaction has already done its quiet work. It means that the future feels open, not because reality is vague, but because it has not yet been constrained. Quantum mechanics does not remove meaning from the world. It reframes where meaning comes from. Meaning is not found in absolute certainty. It is found in patterns that persist, in relationships that endure, in structures that remain stable even when their foundations are flexible. A melody is meaningful not because every note is inevitable, but because the notes follow rules that allow coherence. A life is meaningful not because every outcome is predetermined, but because choices matter within constraints. A universe is meaningful not because it is simple, but because it is consistent enough to be explored, understood, and lived within. The paradoxes we have encountered are not warnings to stop asking questions. They are invitations to ask better ones. Instead of asking whether reality is really real, we can ask how reality organizes itself across scales. Instead of asking where the boundary between observer and observed lies, We can ask how interaction shapes experience. Instead of asking which interpretation is correct, we can ask what each interpretation teaches us about the assumptions we bring with us. And we can do all of this without urgency. The universe is not going anywhere. Its rules are patient. They have waited billions of years to be noticed, and they will wait longer still. There is no need to resolve everything tonight. In fact, there is a quiet wisdom in letting some questions remain open. Quantum mechanics, at its heart, is a lesson in humility. Not the humility of ignorance, but the humility of scale. A reminder that human intuition, shaped by warm days and solid ground, is not a universal measuring tool. A reminder that understanding grows not by forcing reality to fit our expectations, but by allowing our expectations to evolve. And yet, even as our intuitions are challenged, our place in the universe feels more secure, not less. The same laws that allow particles to exist in superposition also allow atoms to form, chemistry to flourish, biology to emerge, and consciousness to arise. The same principles that permit entanglement across space also permit the deep coherence of matter that makes stars burn steadily for billions of years. The universe is strange, yes, but it is a productive strangeness, a disciplined strangeness, one that builds rather than destroys. As you rest now, perhaps letting your thoughts drift more slowly, there is no need to hold on to every idea we've explored. You can let them blur gently at the edges. Like stars fading as dawn approaches, they do not disappear, they simply recede into a quieter background. What remains is a feeling rather than a conclusion, a sense that reality is deeper than it looks, but not hostile. More mysterious than expected, but also more generous. A sense that uncertainty is not a threat, but a space where structure and possibility meet. And within that space you are not lost. You are supported by a universe that knows how to be stable without being rigid, predictable without being dull, open without being chaotic. If your eyes are still open, you can let them close now, knowing that the ground of reality does not vanish when you stop looking at it. If your thoughts are still moving, you can let them slow, trusting that unanswered questions do not need to be carried into sleep. The universe will continue its quiet work. Particles will interact, information will flow, possibilities will narrow into outcomes, all without your supervision. And that is perhaps the final comfort. Reality does not require vigilance. It does not need to be held together by attention. It unfolds patiently and lawfully whether you are awake or asleep. So let this be the end of the questioning for tonight. Not an ending that closes doors, but one that leaves them gently ajar. Thank you for taking this long journey through some of the strangest and most beautiful ideas science has ever uncovered. Wherever your thoughts drift next, and whenever rest finally arrives, may it do so softly. The universe is still here, and for now, that is enough.